So let's imagine you're happily going along and you're taking your limits and you're plugging x values in and everything is working out real nice for you. And then you run into this function f here. And you're like, okay, it's a rational function. I haven't done any rational functions yet, but I'm just going to go ahead and plug in 4 here for f and see what happens. Well, I'm going to go ahead and do this on my calculator. So here's f of x. I plugged in 4, and I get an error. And often I see you guys, when you get an error on your calculator, you don't read what it says. But here it's a really helpful error message. It says divide by 0, right? So the issue here is that the bottom is 0 when x is 4, right? And you may be thinking, well, okay, limit does not exist, right? Which is a good guess. But we already have sort of an idea to describe that. We'd say f of 4 does not exist or is undefined. But that doesn't necessarily tell us about the limit. So I'm kind of stuck here, right? And what I might do, as we often do, often is a useful strategy to look at the graph, right? So here's my graph of f, and notice if I look at x equals 4, it looks like that limit exists, right? So at that spot, and you studied this the first time you saw rational functions, would be a hole in the graph of f, right? So there is a value that the function approaches from both sides, and let's see if we can't find it without looking at the graph. So I'm going to note that my limit is going to be the same limit if I factor the bottom, right? So that gives me x minus 4 times x plus 2, because 2 times negative 4 gives me a negative 8, and 2 plus negative 4 gives me a negative 2, right? And then I'm going to say, well, these two factors cancel out, so my limit as x approaches 4 is equal to the limit as x approaches 4 of just 1 over, and then I can plug in my 4. So notice I solved that problem. I got rid of the bottom, the factor where x equals 0. That was this factor, right? I canceled it out. So once I can plug that in, I know my limit is equal to 1 over 6. 1 over 6, by the way, is about 0.16. So let's see what happens as I walk along this graph, right? So as x gets closer and closer to 4, my x values get closer and closer to that 0.16 until it is suddenly undefined at that point. And then on the other side, well, as I get closer to that point, same thing, 0.166, I get closer to. So when confronted with a rational function, my first step is I can try and plug in a value. And then if that doesn't work, so I get my divide by 0 error, well, then I look for a factor that I can cancel. And then I do the same thing. And then that allowed me to find this 1/6 is my limit, even though the function itself is undefined at that point. Okay, well, while we're on the topic of rational functions, this is also a good time to talk about this limit here. So you read this as the limit as x approaches infinity of f of x. So this was really the question, is like, what happens to this function as we plug in a really big number into x? Well, who knows, right? One way I could try to figure it out is by typing it into my grapher, and then I could look at the table. Oh, and there's my limit at x equals 4 as x approaches 4, right? But I want to know about what happens when these numbers get really, really big. So notice the trend here is as x gets really, really big, my numbers keep getting smaller and smaller, right? And that's also what I see on the graph, right? As I zoom out to the right, my numbers get closer and closer to 0. So in this case, the limit is, well, it's exactly that. It's a limit. So is there a value that this graph never touches? Yeah, there is, right? And it looks like the limit as x approaches infinity of f of x is 0. Okay? We actually already know how to figure that out without graphing. And we'll consider the rule for that here in a second after we do another example. So here I have g of x as x approaches 4. And notice, same thing, if I plug that in here, I get something over 0, right? So that's not going to work. So I'm going to say that this limit is equal to the limit as x approaches 4. I'm going to try to factor, right, of the top factors to x plus 3, x minus 3. It's a difference of squares. And then x minus 4 on the bottom. And notice nothing cancels out here. And I still cannot plug in my 4. So here, this limit does not exist. DNE does not exist. Okay, so these don't always have solutions. And what happened was, let's look at just g, right? Is we actually have a vertical asymptote right at x equals 4 there, right? So it makes sense that that limit would not exist because my x, as x approaches 4 from the left and right, I get very, very different values for y. So these limits won't exist when we have a vertical asymptote. And then while we're looking at our graph of g, why don't we consider as x approaches infinity? So notice if I zoom way out, as x approaches infinity, my y values just keep getting bigger and bigger and bigger. So this limit, well, is infinity. So this idea, the rules for these limits to infinity is called the principle of dominance. And we've already run into this idea before. It used to be called horizontal asymptotes. Now it's called limits to infinity, right? So the idea here is these are just 3 cases. And I'm going to have you pause and copy those down, those examples, just to get practice with writing this notation. The notation here is super important. And then the idea here, though, is very simple, right? So if the exponent on top is bigger, so 3 is bigger than 1, well, that limit is infinity, right? And we saw that just now with g. That was another example of that. If the two powers of x are equal, right? So third, well, then we cancel them out, and the limit is 5 over 2, the ratio of their coefficients. And then if my bottom is bigger, so 4 is bigger than 1, the limit is 0. And we saw that with this guy here, right? That was a limit of 0. Okay, so 2 things at the same time in this lesson, but they're things you already know how to do, and really what we're practicing here is just tackling them using this new notation and this new idea of a limit.